cryptocurrencies and the blockchain. So these are a few different ideas that I decided to put together into a single episode. They're related but distinct. I mean, we could potentially do one or more episodes on each of these topics, but I thought it might be better to give a simpler overview and put a few things together. So we're going to start by talking about the basis of how information is sent securely over the internet, that is RSA cryptography, and then we'll look at the transport layer security system, which is a protocol that underpins the internet today. And then we'll progress to talking about cryptocurrencies and the blockchain, so how that technology works and how transactions are made and how the security arrangement works, and conclude by looking at some of the pros and cons of cryptocurrency as a currency. So if you like, the first part of the episode will be focused on the crypto part, and the second part of the episode will be focused on the currency part, if you want to think of it that way. There are no recommended pre-listening prerequisites for this episode, so we can just jump straight in and begin by talking about RSA cryptography. So cryptography is the science of sending and decrypting information in a secure way, or storing information securely as well. And particularly the issue that we're interested in here is the use of cryptography to send information securely over the internet. The key issue is, how can you ensure that one person sending a message to a second person? In cryptography, the two communicating parties are traditionally Alice and Bob. So the question is, how can Alice send a message to Bob in a way whereby Alice is sure that the message was delivered, that the message wasn't corrupted, and that Bob is the person who actually receives the message and not anybody else? And in particular, the question is how that can be ensured even when the message is sent via a publicly accessible medium. So an example could be if you're sending a radio message, or if you're sending a message over the internet, or over any medium really where there's a possibility of interception or of snooping on the content of the message. So that's what cryptography is about, at least in the context that we're interested in it here. RSA cryptography, as I mentioned, is a particular approach to cryptography which forms the basis of many of the most common systems used in the internet, as well as in many cryptocurrencies. RSA is an acronym comprised of the letters of the surnames of the three individuals who devised the algorithm in the 1970s. So I'm just going to call it RSA for short, which is pretty standard. The basic idea here is that RSA cryptography relies on the difficulty in factoring large numbers, particularly large prime numbers. This is called the factoring problem. The essential idea is that certain mathematical operations are easy to perform but very difficult to invert. And finding the factors of a large number is a good example of this. If I ask you to check whether or not two numbers multiply to give a third number, well, that's very easy. You just times them together and then you see if the number that you get is the same as the target number. That's extremely simple to do. Conversely, if I ask you to find numbers that multiply together to give a target number, in other words, find the factors of this number, that can be quite difficult, especially if the target number is quite large. So there's this asymmetry here between how easy it is to check an answer and how easy it is to generate that answer in the first place. Or in other words, how easy it is to compute a function and how easy it is to compute the inverse of that function, like going in the opposite direction. And this is the basic idea behind RSA cryptography applied to the problem of finding or of factorizing large numbers. Functions that have this property of being easy to perform but difficult to reverse or invert are known as one-way functions. Now, there's a bit of complexity here about whether or not one-way functions truly exist mathematically, because we don't currently know whether there are any ways to quickly invert these one-way functions, like for example, to quickly find the factors of very large numbers. No one has been able to prove that there is no relatively fast way of doing this in polynomial time, for those who know about such things, but don't worry if that doesn't make any sense to you. So it's not proven that these one-way functions exist. It's more that no one has figured out a way to readily invert them yet, and so the system is relied upon as probably in practice being very difficult to invert and find the factors. So it's important to bear in mind that these systems are not provably secure, they're just widely thought to be quite secure. It is possible that someone could come up with an algorithm that allows you to quickly invert these one-way functions and thereby undermining the security of the system, as we'll explain in a moment, but that's thought to be quite unlikely. Anyway, so we've got these one-way functions based on factorizing large numbers. So a one-way function is one where it's easy to compute one way, but very difficult to compute the other way, or at least as far as we know, it's very difficult to compute it the other way. And so that's really handy because what it allows you to do is to generate two numbers, one of which is called the public key, another which is called the private key. So there's your public key and your private key, and these are just both big numbers, like very large numbers that are generated in a certain way. The actual mathematical formalism that's used in RSA public key cryptography is called modular arithmetic. So this uses properties, the remainder that's left over after you perform division. So for example, if I take 13 divided by 7, 7 goes once into 13, and 6 left over. So we would say that 13 mod 7 is equal to 6, as an example. So this modular arithmetic has a lot of mathematical properties that make it very suitable for deployment in cryptography, and that's the actual mathematics that underlies the operation of the system. That, however, is too technical to explain in detail here, so instead I'm going to simplify things rather dramatically, but preserve the key intuition behind it. We can think of it this way. To generate my private key, what I do is I randomly select two large prime numbers, and then I multiply them together to get a third even bigger number. So this third really big number is used to be my public key. It's called public because I can tell everyone my public key. In fact, that's the point of it. You communicate it to everyone, and that's how people can send messages to you. They can use your public key. What makes this system secure is the fact that while everyone can see your public key, and it's very easy for you to generate your public key, you just multiply your two prime numbers together to get your public key. That's trivial. It's very difficult for anyone to go back. That is, it's very hard for anyone to work out what your private key is given your public key, because your private key is let's say one of those two numbers that you multiply together initially to get the public key. It's easy to do that. It's easy to go forwards, but it's very hard to go back. This is the non-invertible function that we talked about. You can then use your private key, so one of these prime numbers that you selected, to encrypt messages that you want to send people. Or alternatively, you can use it to decrypt messages that people send to you. In cryptocurrency, we describe an unencrypted message as plain text. So you type on the keyboard and each character is assigned a number, and then you can write any string down that I want to convey as a long span of numbers. I can then encrypt that by performing a mathematical operation on it to convert from the plain text to what's called the ciphertext. So that's the encoded version or the encrypted version. And the encrypted version, the ciphertext, will appear random to anyone who is trying to snoop or spy on the message that I'm sending, or the message that someone is sending to me. The ciphertext isn't truly random. It's generated in a deterministic way. It's just that it's very difficult to work out what the pattern is if you don't have the secret private key. For someone with the private key, it's trivial. They just perform a simple mathematical operation using the private key, which converts the ciphertext back to plain text and therefore allows them to read the secret message. But for anyone who doesn't have that private key, there's no way for them to do that. They could theoretically try to guess all the possibilities of the private key, but that's why we use very large, often 256 or 512 bits long, in order to make it virtually impossible that anyone can just sort of brute force it. It would take, longer than the expected lifetime of the sun in order to do this by brute force, by just checking all of the possibilities, and so practically that's impossible. The only other way they could do it is if they found a way to calculate the private key from your public key. But remember that the whole point is that we use a non-invertible function, so that that's also, as far as we know, practically impossible. We don't know of any such functions that allow you to do that. The key thing to understand here is the centrality of the non-invertible function, or the one-way function, for the system to work, because it's what allows me to easily generate a public key and share that to people, and then they can use that public key to encrypt information that they want to send to me, and I can use my private key to decrypt that information and read it, convert it back to plain text. But no one can take my public key and reverse engineer or work out my private key from the publicly available public one, because doing so would involve inverting a non-invertible function or going backwards on a one-way function, which is practically speaking impossible. And that relies fundamentally, as we said, on the difficulty in factoring very large numbers. So there's a lot of detail to it surrounding the precise way in which these things are calculated using modular arithmetic. I'm not going to try to explain that. But the basic principle is that you choose a large prime number, which is your private key or the basis of your private key. You then use that to compute a public key. Going forwards in that way is very easy. You tell everyone your public key. They can use that public key, perform some mathematical operations to encrypt messages they want to send to you. To anyone who doesn't have your private key, the messages will look random as gibberish. But to you, because you know how it was encoded and it was encoded using your public key, you can use your private key to decrypt it and read the message. But no one else who doesn't have your private key will be able to do that. In order to do that, they would have to be able to work out your private key using your public key, but that's essentially impossible because it's very difficult to factor very large numbers. So that's the key of how public key cryptography, RSA cryptography, works. Now, I've mentioned that you can use your public key to broadcast that to people and tell people, hey, use this to encrypt messages to send to me, which you can then read using your private key. That's one use of the technology, but you can also use it to send messages or to digitally sign messages. So I can use my private key to sign a message and then send that to everyone so that everyone can verify using my public key that I have signed it, but no one else can produce